All right, so let's get started. Just nothing really new to report here. ICAL is out and available. I forget if it's, I meant to double check if it's due Tuesday or Thursday, but whenever the day is due, we'll just go with whatever's date is on Canvas. I'm a little confused because of this semester's Veterans Day falling on a Thursday, I had to kind of combine the last two lectures into one lecture. So the last kind of technical lecture will be Tuesday, then there'll be the Thanksgiving break. And then the Tuesday after that will be lecture M, which is the final exam review lecture. And so this ICAL is intended to be due before lecture L, but because K and L are, K2 and L are kind of combined, then I forget when it's actually going to say that it's due, but we'll go with whatever's there because it's had that due date all semester. Homework J2 is out there. It was originally due today, and it's still technically due today, but I've relaxed the late policy. So if you turn it in by Monday night, there'll be no penalty. So if it's a little bit different than the other homeworks, all the other homeworks are sort of two problems from the text where you kind of work things out by hand. And in this one, it's an arena-based homework. I'm giving some people some hints over email. One thing I might mention is if you're having trouble figuring out how to make it so that you prevent there being more than one outstanding order at a time, then I guess I would encourage you to look at depending on whether you're using the old blocks or the new blocks, the kind of the equivalent of the little decide block that decides what to do with the inventory persons they come in, and also the assign statement that happens kind of before and after an inventory order goes out. So you can play with those three elements, and you should be able to make it so that while an inventory order is out, you can prevent a new inventory assessment from happening. And so you might have to create a new global variable to do that. You might have to play with some of the existing ones. There's a bunch of different ways you could do it, but that's where I would recommend you take a look, is that side block and then an assign statement kind of just as the inventory order is made, and the assign statement that happens just after the inventory is made, order is received, and the inventory gets changed. So those are kind of the places that'd be where I would choose to make those changes. Again, more than one way to do it, but that's kind of where I would look to do it. So that's my tip for that. You can feel free to do the optimization manually if you'd like. You can also try the process analyzer or OptQuest. That's up to you, but the manual is fine as well. Otherwise, you know, now that lab 10 is kind of out there, we have no more labs after lab 10. So the rest of the kind of lab time in this semester, or in the course, is meant to be time for you to work on the final project. So the final project, just make sure you're kind of working on a model where you can, don't have to be too ambitious, but you just want to kind of be able to show me a simulation where you've run and generated interesting and illuminating results that tell you about some interesting aspect of the system that you probably couldn't have guessed with high confidence before you ran the simulation. So that's kind of, you know, the salient features there. The timeline here is, so again, we've got this lecture, we've got a lecture on Tuesday, upcoming Tuesday, then there's the Thanksgiving break. And then that week after that, that is the week that your presentations and your report projects, your reports will be due. And so Tuesday we'll have our final exam review lecture. The Wednesday of that week, that night, Wednesday night, is when the presentations and final reports are due. And I don't have a grace period on those because right at midnight, Canvas automatically does the peer review assignment. So by 11:59, you turn in your presentation and your final report. And then you've got Thursday, Friday, and Saturday will be the time you have to read one other group's report and watch one other group's presentation, and then fill out those peer reviews. So that's the kind of process there. Then Thursday of that week, that'll be stage one of the final exam. Then you'll get the weekend, and then when we come back in finals week, then the day that we're assigned in finals week, which I'd have to post on Canvas, but I don't know off the top of my head, I think it's Tuesday, that will be the day for the stage 2 exam. And I'll go ahead and do the same thing I did with the midterm, where I'll give you Thursday, Friday for the stage 1 exam, and I'll give you, I guess maybe Monday, Tuesday. I guess if I wanted to keep it in parallel, it would be like Tuesday, Wednesday, I'll kind of mull over that. If you have strong feelings on whether you'd want your stage 2 to be Monday, Tuesday, or a Tuesday, Wednesday, send me an email and I'll take that into consideration. Yeah, so that's kind of the schedule there. For studying for the final exam, if you do that lockdown browser compliance test, and see there might be a question in the chat, I'll take care of that in just a second. That lockdown browser compliance test, if you do that, that's like kind of like, it's called module unit M.1, and that's all it has in it. Once you do that, that'll unlock unit M.2, and that module has all of the final exam resources in it. And one of those resources is the ICA-M, which you should do before the final exam review lecture M. And that just randomly samples from previous ICAs, and you can take it as many times as you want, and it'll take the highest score. Once that ICA is gone, the practice version will be put in its place. If you want to go back and study pre-midterm stuff, the pre-midterm practice is also available. There's a bunch of sample final exams from previous semesters that are also online in that module. And then a couple of other little things there too. So, oh, and this is outdated. So there is no retake. It's a stage 2 exam. Question, yeah? This is K1, and then K2 and L will be combined. And again, I'll just also type that into the chat. The retake on current slide is a holdover from several semesters ago. It needs to be updated for 2-stage. There is, all right, and so then there was a question in the chat about the homework where he said, if there's an outstanding order, does the evaluator need to wait for the beginning of the next day to create again? And that's fine to do that. Is that for the homework, one way to prevent having 2 orders out in a row is if a new order assessment comes in, if there's an outstanding order, that new assessor can just disappear and just wait for the next assessment period. So you don't need to like queue up your assessors or where they're like waiting to now check on the inventory as they're waiting for that. And you can sort of assume that while the inventory order is out, inventory assessments just cease. And then that definitely prevents you from having any new orders. So that's a fine way to solve that problem. All right, so any other questions? Okay. Great. All right. So the big, at this point, we are trying to sort of get you to be at the point of the class where I don't want you to summarize any of your data with point estimates. So you want to break the habit. This is was remade, but back when I saw it, it was 1991. When young Keanu Reeves was out. Point Break has nothing to do with point estimation, but I just like the juxtaposition of point and break. So this, whenever you take data from your simulations or the real world, you shouldn't ever just take an average and report the average, because that average is a sample average. It has no relationship to the population average. So you always have to then give an interval. So on your final reports, wherever you're reporting data from samples, you should always report intervals. And that even goes with things like regression coefficients. And so if you're plotting relationships between things and you fit a regression line, then any good statistical tool that allows you to plot a regression line will allow you to plot a confidence interval on the regression coefficients. And if 0 is included in your regression coefficient confidence interval, and that means that you can't reject the possibility that there is no relationship between the variables. And so, so use confidence intervals everywhere. And usually you're looking for these critical things, like is 0 included in the confidence interval? Or is my favorite pet theory included in the confidence interval? This is an example I gave last time where there was a pet theory about the relationship between the scaling of ant colonies and the energy that they use, and a null. So there's the null hypothesis, is no relationship, which would be 0, which is outside the confidence interval. But then sort of the kind of naive hypothesis, which is sort of like a null hypothesis, is that they would scale at the same rate together. And so 1.0 would be kind of the what you might expect naively, and that's outside of the confidence interval. And so this data here shows that there is a relationship between these two things, which isn't that much of a surprise, but the relationship is it's sublinear. And so that was something that was an important contribution from this particular paper. And moreover, a pet theory people had that it would be sublinear, and not only be sublinear, but the coefficient would be 0.75. That's included in the confidence interval they found from data. So these data not only exclude, you can be confident that it's not linear and it's not zero. It also gives you a little bit of evidence to say, and by the way, that theory you have about the 3/4 scaling, yeah, that's consistent with these data. So it's always really important to summarize things with these confidence intervals. And so in the context of simulation, we talked about absolute performance estimation. I've got a single model of a system, a call center here, and I want to do something like say, how do I estimate the performance of this call center in this configuration? So I have this single model, I run R replications of that model, I get a sample mean out of those R replications and a standard deviation, and that mean alone is not a good estimate of the real system. And so I have to put a confidence interval around that and then ask questions about the confidence interval. So that's what I do with absolute performance estimation, is I have my mean from my simulation right here in the middle, and this mean from the simulation, maybe this guy. So the mean from the simulation here, I then put this confidence interval around it. So that's this kind of bar here. And what I find here is that any performance estimate that is in the confidence interval, I cannot reject. So that's a possibility for the true performance of the system. But pretty confidently, I can reject any performance estimate that's outside of the interval. So if I have a certain hypothesis that's outside the interval, like this one here, this might be a benchmark. I might want to say that my configuration does better than your benchmark. You said you wanted me to build a call center that would give wait times that were less than 5 minutes, and 5 minutes was the benchmark. Well, I can say I ran my experiment. I can't tell you exactly what the wait time is going to be every single time this call center runs, but I can tell you for sure that the average wait time, the confidence interval does not include 5 minutes. So we are different than 5 minutes. And then in this case, you're above 5 minutes, which kind of sounds bad, but you can imagine if the confidence interval is below 5 minutes, then you can say, we are confident that we are lower than the benchmark. We have met your condition and done better than that. So this is kind of the right way to take your data here. Use those confidence intervals. Don't just use the means. You got to use the whole interval and then think about what that whole interval means there. Now, when you calculate these confidence intervals, what we're moving toward from absolute performance estimation is into relative performance estimation, where we're not just saying, do I beat 5 minutes? I'd say, does this system beat this system? But we're going to use the same confidence interval framework there. So the only thing that's going to change as we move from absolute to relative is how we calculate the degrees of freedom in the t, the critical t value, and how we calculate the standard error of the mean. Those are the two things that, if you have those two things, you can calculate any confidence interval. So for the absolute performance case, it's easy. The degrees of freedom are just the number of samples minus 1. And the standard error of the mean is just the sample standard deviation divided by the square root of the number of samples. So you can take those two things and you plug them into the half-width formula, which has got that critical t value with your alpha in there. It's got that standard error of the mean, and you got your confidence interval calculated. If you've calculated a 95% confidence interval and somebody says, actually, I wanted a 90% confidence interval, you can do this little scaling here where you can take that 95% half-width and you can scale it. You basically divide by the critical t value for 95% confidence interval and then multiply by the critical t value for 90% confidence interval. And you're in good shape there. So, and this actually looks like a typo. That, of course, shouldn't be 0.9 there. That should be alpha over 2, which in this case will be 1 minus 0.9. So that should be 0.1 and 0.05. So I'll go back through and fix that. But it's the formula up here, the alpha there. So a 95% confidence interval is a 5% alpha. And then if somebody says, we want to make sure that we have a certain sensitivity, so they're saying that, your boss tells you, I know your simulation can't give me the actual performance of the system. It'll give me an interval of possible performances, but I want that interval to not have a half width that's no more than a minute in terms of wait time. Well, then now you know that, well, if I've run a pilot study with a certain standard deviation, I now have a formula that allows me to say, based on the variance that I've estimated, or the standard deviation I've estimated from my pilot study, and the 1 minute half width that my boss has given me, I can now say, I'm going to need roughly 100 replications in order to come down to the sensitivity that my boss wants me to estimate this performance with. And I can plug that in, figure out how many replications, say it's 100, subtract off the few replications I've already run in my pilot study, and run the balance. And then I hopefully will meet the half width requirement. So that's absolute performance estimation. Are there any questions about this general process here, where we're running replications, we're presenting confidence intervals, and we're comparing confidence intervals to points in order to make interesting conclusions? That makes sense? And we are just going to scale this up to the relative case. So the relative case, we've got two model systems now. We've got maybe a representation of our current system, our as-is system, and we've got a proposed system. And this proposed system uses cross-training, for example, so that we don't have to have a whole separate billing department and a support department. We just group them all together, and maybe we'll get less idle time because now our billings are sitting there idle so much that if they just knew how to provide support, they could really help out our support staff, or vice versa. So we want to compare these things together. So we run a certain number of replications of one, a certain number of replications of the other, not necessarily the same number of replications. We get a mean and a variance for both, but we then need to think about them in kind of this interval perspective here. So when we think about comparing two systems together with one interval, we think about the interval of their differences. And so we say, what is the confidence interval that represents system 1 performance minus system 2 performance, plus or minus the half width for that quantity right there? So rather than thinking about how am I comparing one system to another, what I'm doing is I'm sort of saying, how do I compare their difference to 0? And this framework allows us to think about relative performance estimates exactly the same way as we thought about absolute performance estimates. But instead of now estimating a wait time, we're estimating a difference in wait times. And so then we can say, does this difference in wait times include 0 in the interval? And if it does, the systems are equivalent to the level of sensitivity given by our half width. If it does not, then we can say that one system is better than the other, which depending on which side of 0 the confidence interval lives on. And so, but we have to change the formula for degrees of freedom and standard error of the mean based on the type of experiment that we run. And so that's what we need to learn, is the formulas for those two quantities based on how you run the experiment. And so there's 3 different ways that we consider. And the first way is kind of like homework G3, where it's a paired design. And so I'll show that here in a second, but we're basically going to run the same input into both models and look at the outputs that are paired up for each input, and then look at those differences. If we can't run the same inputs into both systems, so we're going to run different inputs into both systems, then we have to use a different formula for the degrees of freedom and the standard error of the mean. But we need to know, do the two models, model 1 and model 2, do their performance variables have the same variance or a different variance? If they have the same variance, we use what's called a pooled variance t-test version of this confidence interval. If they have different variances, we use a Welch's unequal variance t-test. And so there's just 2 different formulas. Once you drop the formulas in here, you interpret the confidence interval the same way. So let's look at that. So in the first case here, this is when I run the same input into both systems. And for each input, I look at an output from system 1 and output from system 2, and I calculate that difference. For another input, I look at the output of system 1, output of system 2, calculate a difference, and so on. This is just like in homework G3, where we said we took real data from the real system and we ran it into the simulated system. So we had a real Monday, generated a simulated Monday with the same customers. And then we had a real Tuesday, and then generated a simulated Tuesday with the same customers, a real Wednesday, simulated Wednesday. And for Monday, we could say, what was the difference between the simulated Monday's performance and the real Monday's performance, and vice versa. So then we got a Monday difference, a Tuesday difference, a Wednesday difference, and so on. And then for those, we could say, if we generate a confidence interval on the weekday differences in performances, does that confidence interval include 0? That's basically what we're doing here. So they have the same number of replications for both systems, model 1 and model 2. I'm just going to call it R. We're going to put the same input into both systems. In homework G3, we got the input from the real world. What we'll do, as we'll see a little bit later today, is we'll use the same pseudo-random number generator seed in both systems. So if simulated model 1, simulated model 2, they use the same seed in both systems, and that's going to generate the same customer streams or caller streams for these two systems here. And that is going to pair those outputs together. And then for each output, we can calculate a difference. And so for each input, we can calculate a difference in outputs, and that will generate a string of differences. So every replication will have one difference value associated with it. So if you got 10 replications, you'll have 10 differences. And then we compare the confidence interval on those differences to 0. If they include 0, the systems we can't tell a difference between. If they don't include 0, then one system is better than the other. So if I want to calculate, in this case, the variance in differences, well, the variance in differences here, a variance in two variables. So if you go back to just laws of probability, the variance in the difference of two random variables is just the variance in one random variable plus the variance of the second random variable minus 2 times the covariance, which is like a correlation term between the two variables. Now, in our case, because we have, if we did not run the same inputs into both, then this covariance term would be 0 because there'd be no relationship between model 1 and model 2. But because we're running the same inputs into both, we are inducing a correlation between them, which if that correlation is positive, so when things get harder for system 1, they get harder for system 2, that has the benefit of reducing the variance on this difference. And that reduced variance gives us more statistical power. And that's the reason why we do this whole crazy process up here of pairing the outputs together based on the same input. So that's kind of the theory that is going on here. So, so that's the theory of why we would do this. Now, what does it look like in principle? Well, like I said, for every replication, you calculate the difference between the performance of replication model 1, performance of that replication in model 2, and then you can calculate a mean difference across all of your replications, and then you can calculate a variance across all of your replications of those differences. And then we've got the degrees of freedom here are still going to be R minus 1, just like they are in the absolute case, the single performance estimate case. But then our standard deviation is also going to be pretty much what you'd expect. It's just the standard deviation of the differences divided by square root of R. And then we can calculate a confidence interval on the differences. And so this is really identical to the absolute performance estimate, but instead of estimating a single model, we kind of turned the two models into one model because we've paired their inputs together. It's almost like you had a model, you drew an arena model and you copied and pasted another arena model underneath it. You ran the same inputs into both, and then you connected the outputs together. But in reality, you could run it inside one big arena model. So really, you've turned two simulation models into one model, and that's why this looks identical to all the formulas that we were using to calculate our conventional intervals. So this is how we do it for the paired case. Now, any questions about the paired case here, about what, we haven't really done much here, but instead of running a confidence interval for one system, we ran the two systems in parallel with the same inputs, generated a difference, and then generated a confidence interval on those differences, as if the two systems were one system. And then if 0 is included in this interval, then the systems can't be told apart. If 0 is excluded from the interval, one system's performance is greater than the others statistically. Okay, now where it gets interesting is what happens when we can't do that pairing. In this case, we really are running the two models independently of each other. So we don't have the ability to reduce the variance by introducing positive correlation. And so the idea here is that let's imagine that my two model systems will run with different inputs, but let's say that we can assume that the variance coming out of the performance for model 1 is identical to the variance coming out of the performance for model 2. And we can test for that. There are tests for that, like Levine's test or an F test. Like there's a bunch of different tests you can do that will test to see, are the variance of these two data sets the same? And so if the variances are the same, then to calculate the variance, what we can do is combine together all of the data across the two models just for the purposes of estimating variance. And so, and that's kind of what we've done down here. And so this is the variance for system 1 or system I. You can also think of the variance for system 2. And if I wanted to pool all of that together, then my variance for the pooled system, where I just pretend like all of the systems, I've just put them all in one bucket and then calculate that variance, is going to be this formula here, which if you kind of squint at it, then you can kind of tell that all you're doing is rescaling this term. You're getting rid of this term from the individual calculations in both of these cases, and then dividing by a new denominator, which includes all the replications from model 1 plus all the replications from model 2, but then you subtract 2 degrees of freedom because you lost a degree of freedom for both models, because one model you used its mean to calculate this, the other model used its mean to calculate this. So it looks very similar to our normal variance equation, but we have the degrees of freedom is a little bit different. And so with that in mind, you can actually take this and simplify it, and an estimate of this term here for the standard error is just the standard deviation of the mean times the square root of 1 over the number of reps for model 1 plus 1 over the model reps for model 2. For a relatively high number of replications, this estimation, this here is identical to this one up here. So you could calculate this one, but it's just simpler to calculate this one. So this is typically the formula we use for the pooled variance example here. But when we calculate our critical t value, we have to use this as our degrees of freedom. So instead of using R1 minus 1 or R1 plus R2 minus 1, we have to use R1 plus R2 minus 2 for the critical t value to calculate the half width. And then the standard error we use in the half width will be this standard error formula down here. And this right here is going to be more powerful than the unequal variance method that I'll show you in the slide or two, especially for low sample sizes. And so if you can make this assumption, you get more statistical power. But if you can't make this assumption, you have to go with methods designed, as I'll show you in the next slide or two, for unequal variance. So I've got two independent systems. I can assume they have equal variance and performance. This is how I calculate their standard error of the mean. This is how I calculate their degrees of freedom. I plug those in and I can calculate the exact same confidence interval just with these updates here, and then compare it to 0 in order to compare the two systems. Any questions about this, what I mean by these things? Two model systems, two simulation models, same variance in the output performance. This is how to calculate that confidence interval. All right, so then you could say, well, what if I run my two models and one model has a really tight distribution of values and the other one has a really wide distribution of values, so they do not have equal variance. So for whatever reason, whatever intervention you made in model 2 actually maybe created a lot more variance in your performance or vice versa. So in those cases, I can't use the pooled formulas. So I have to use I have to actually kind of estimate the standard error of the mean without any approximations that have to do with them having the same variance. And so the standard error of two independent systems is going to be the square root of the sum of their variances, because there's no correlation between them. So it's a pretty sort of easy calculation there. So if I do a little bit of simplifications here, then what I find here is that the standard error of the difference in means is just the square root of basically the variance of the two systems. So you can think of this as the standard error or the variance of the mean for model 1, and this is the variance of the mean for model 2. And so I add together those two variances. So in other words, if you think about this little term here, if you took its square root, that would be the standard error of the mean for system 1. If you took this guy here and its square root inside the quotient here, then that would also just be the standard error mean of system 2. So I'm effectively just adding the variance of the mean of the two systems together and then taking their square root. And that's how I calculate the standard error of the mean. So for the unequal variance case, for the Welch's unequal variance, the standard error of the mean is a pretty simple formula. It's kind of a very straightforward formula. Unfortunately, the degrees of freedom is not. And I am not going to go through the derivation of these degrees of freedom, but you can work out why this is a good approximation for the degrees of freedom. But so you have this formula, and if you were to calculate this confidence interval, you would just look this formula up, or you'd have a program like R or whatever calculate it for you. And this formula is just a formula of the sample variances and the numbers of replications, and it will then end up giving you a number out, which depending on the difference in sample sizes and the difference in variances might be very close to R1 plus R2 minus 2, or it might be very different than that. But so it allows for, it's very flexible in the degrees of freedom. Once you have that, you can now calculate a half width, because you can now plug this and into the critical t-value, so your degrees of freedom and the critical t-value, you multiply that critical t-value by the standard error of the mean given by this, and you can now calculate a half width. So this is a lower power approach, but it can be used in more cases. So when you really can't assume that your two variances are the same. So for all three of these, I've given you a formula for standard error of the mean. I've given you a formula for degrees of freedom. You know the formula for the center of the half width. That's just the mean of the first system minus the mean of the second system. So that will be the center for all of these. So you know the point estimate of the difference of the means. It's just the difference of one system's sample mean minus the other system's sample mean. This is how you calculate the half width, by using these. So you plug in the standard error based on the type of experiment you've run. You plug in the degrees of freedom based on the type of experiment you've run. You get a confidence interval on the differences between the two systems. The mean of system 1 minus the mean of system 2, the sample means there, the half width using these, and then you can compare the confidence intervals to 0. If the confidence interval is on one side of 0, you can say one system is greater than the other. If it's on the other side, you can say the opposite. If 0 is included in the confidence interval, there's no detectable difference between the systems. And if it is your job to detect which system is better, you might need to generate more replications. So you might need to sample more until you can come to some conclusion as to which system is better. And so that's the general process here. I think the next slide is sort of summarizing the same thing here. So this slide, I think this is the slide from the previous lecture. This is my version of it from what was intended to be this lecture. It's the same exact thing here. Here's a depiction of the confidence interval, comparing it to 0. Confidence interval has a half width, which depends on the degrees of freedom and the standard error. If you use a paired design, your degrees of freedom and standard error are these formulas. If you use an unpaired design, an independent design, but you can assume that the variance in the two performances are the same, these are the formulas you use. If you use an unpaired independent design, but you can't assume equal variances, then these are the formulas you use. Regardless of what formulas you use, you plug them into the half width formula, You get a confidence interval around the means here, the difference in means, and you compare it to 0. And that's how you can compare two systems together rigorously. So any questions about this process? Just comparing two systems in a statistically rigorous way, given that both systems are just samples of a real world system. Okay. That's what I mean by relative performance estimation. All right, and people do this in the real world, I'll promise you that. So this is taken from an academic paper where they did a paired example with these two systems. And right in the text of the paper, I won't read through all of this sort of stuff here, but they point out that they did they give a t-value. They say it's not significant. They give you the number of samples. They say they did a paired t-test, and then they report the mean difference. So this is the center of that confidence interval is negative 0.071. The 95% confidence intervals go from negative 0.2 to positive 0.061. So right there, they're saying we calculated the difference between these two systems, and the resulting confidence interval included 0. Consequently, we could not conclude that these systems were any different. But in a different experiment that they ran down here, testing something else, then they said that they ran another paired t-test, and they reported their t-value, the test that they used, the number of samples, and they said our mean difference here was minus 0.2, but they gave the confidence intervals go from minus 0.4 to minus 0.04. So here the confidence intervals are all negative, so they do not include 0. So they say that they did get a significant result in this group. So you can sometimes, all you do is list the confidence intervals, and that's enough to convince your reader that you've shown a significant difference between the systems. And that's what that's one thing you can do with in text when you've got one of these designs. If it really is a paired design, graphically, it's common to show your results this way, where you've got, in this case, I took it from a scientific paper, so colony is on the x-axis. In your case, it might be replication. And so if you've got two systems and you ran however many replications, let's say 10 replications, you can have replication 1, and you can say that the circles are system 1, the X's are system 2. And so for system 1 on replication 1, using the same customers that that we have for replication 1, system 1 got the 0 and system 2 got the X. And then you can do that, well, then for replication 2, replication 3, and you do it for all of these replications. And if you notice that all of the circles are lower than all of the X's, then that probably means that model 1, which is associated with the circles, is going to have a lower performance across all of these different cases. And so you can take all of these differences here, these differences between the X and the O's, and you could actually, and I thought I had that on the next slide, but you can actually then plot a bar plot or a box and whiskers plot just of those differences. And that will then summarize that, oh, the differences here are all, most of them are positive. So there was one where the trend was flipped, but the rest are positive. And a paired t-test, which is just going to be a t-test on those differences comparing to 0, will probably reject 0 as a plausible hypothesis. So you will be able to show that there's a difference here. Now, if you couldn't do a paired design, so you really ran one model system with a totally different set of inputs than the other, then really you're limited to this sort of box and whiskers plot to summarize your results graphically. So this is something I took from another scientific paper where they had a group that was less than 45 and a group that's greater than 45. You would say, I've got my as-is system, I've got my intervention system, and I'm plotting the box and whiskers plots for the performance variable from the as-is system and for the intervention system. And if I were to do a 2-sample t-test, then that might show that there is a difference between these, which would be a p-value less than 0.05. And I can see that graphically as saying this box and whiskers plot looks like it is lower than this box and whiskers plot. Another option you'd have is just to plot the confidence intervals. If I were to plot the 95% single confidence interval for this system next to the 95% one sample confidence interval for this system, then they probably won't overlap, which would be a quick way for me to, to actually get around not going through doing the full t-test. So this is one way to summarize your data. If you wanted to, you could also just plot the two sample confidence interval. But a lot of times with these two sample things, people just like seeing the box and whiskers plots for the populations and then seeing a p-values. So that's another way to summarize these data. So it's like 3 different ways to do it. You can just report confidence intervals in text. You can show in a paired case per replication differences. And in the unpaired case, you can even just do box and whiskers plots for all of your data and then just report p-values. These are all legitimate ways to summarize these results. Okay. So any questions about these cases here, which are for comparing 2 systems? Okay. All right, so all that is kind of a summary of where we've been going so far. What we haven't talked about quite yet is then what about 3 or more systems? So I've got I might have an as-is system, a proposed system, and another proposed system that's sort of optimized. And so your boss comes to you, they say, I need you to build a simulation model of our current call center. You say, fine, our current call center has billing operators and support operators. And then they say, we are considering cross-training everyone. So instead of having 7 operators split like this, we'll just have 7 operators doing generic billing support together. And you go, okay, fine, I can build a simulation for that. And then they say, but it's possible that we will be so efficient that we actually won't need 7 operators anymore. We'll actually be fine paying for 6 operators. And then so they might ask you to build a 3rd system where you go down to here. And so then the question would be, can we actually get less wait time for our callers with fewer operators if we cross-train? That would be kind of the question. So now I need to compare 3 different systems: the as-is system, the cross-train only system, and the cross-train and then the reduction in force. So I run our replications are, there could be a different number of replications for all 3. I get a sample mean for all 3, a sample variance for all 3. How do I then statistically rigorously compare these things in sort of a, I don't want to say it, in a statistically rigorous way? How do I compare all of these and rank them together? And so this falls under the topic of ranking and selection approaches in statistics. And so there's the naive way to do ranking and selection, is I compare all of the pairs together. So I could do my 2 model comparisons that I just was talking about for every pair here. I could compare 1 to 2, 1 to 3, 2 to 3. I think that's it. And so but you could go through and you could say, whatever the 3 choose 2 combinations there, I could compare all of those. And so, so if I have K systems, so in this case, 3 systems, 3 times 2 divided by 2, 3 different comparisons. So I could compare each one of those together. And if I found that there was a significant difference between 1 and 2, and a significant difference between 2 and 3, and a significant difference between 1 and 3 that was consistent, then I might be able to rank these things and be able to say 1 is lowest, 2 is intermediate, and 3 is highest, or something like that. If I was able to show statistical differences between the 2. I might show that I can see a difference between 1 and 3 and 1 and 2, but I can't tell a difference between 2 and 3, in which case I'd report to the boss, 2 and 3 are better than 1, but I can't tell a difference between 2 and 3, so it's kind of up to you. Or the difference between 2 or 3 are so small that it's not worth the headache of going to system 3, you may as well just go to system 2, or vice versa. So this would be one way to do that, to do all of those comparisons. The trick with this, though, is when you generate that confidence interval for each one of those pairwise comparisons, you've got to do that Bonferroni thing that I was talking about earlier, where you divide your desired alpha for the whole system by the number of comparisons. So if you did 3 comparisons, then the confidence interval you generate for each pairwise comparison is going to be 0.05 divided by 3. So you're going to get a reduced alpha. So that reduced alpha is going to result in a larger confidence interval for each pairwise comparison. And that's necessary so that you don't accidentally detect an ordering at a rate that is higher than your 5% false positive rate. Because kind of the false positive rate for ranking and selection is the probability of detecting an ordering when all the systems are equivalent. And we want that to be 0.05. So you don't want to accidentally tell your boss that system 2 is best when all 3 systems were the same, because in that case, you might as well just stay with the as-is system. Why go through the headache of updating the system 2? You don't want to do that very often at all. The only way you guarantee you don't accidentally tell your boss that system 2 is better when they're all equal is by inflating the confidence level or deflating the type 1 error for each pairwise comparison. And that's, we have to do that to avoid the so-called fishing problem. So you don't accidentally find a difference just by chance. So that's the naive way to do ranking and selection. Are there questions about this general idea about doing a bunch of pairwise comparisons, but then counting up how many pairwise comparisons, and for each comparison, reducing its alpha by the desired alpha divided by the number of comparisons? That's the so-called Bonferroni approach. Okay, now the better way to do that would be to do an ANOVA. And so in an ANOVA, I could, which you should have talked about in like 380, 385, possibly even in 474. In ANOVA, I could put in my my different systems, and that would be kind of like the different groups down here. So I could have a model 1, model 2, model 3, model 4, model 5. And the beauty of an ANOVA is, without depressing your statistical power, in one shot, the ANOVA can tell you if a difference exists among this group. So are all of these groups equal, or is there some ordering? That's what the ANOVA immediately tells you. So if P is less than 0.05 for an ANOVA, you've detected an ordering. You don't know what the ordering is, but you know that an ordering exists. They aren't all equal. So then your next step is, after your ANOVA has told you there's a difference, you can only do it then, you do what's called a post hoc test. And you'll be able to go into JUMP or SAS or SPSS or R, any tool that does an ANOVA will also have a post hoc test. And you run that post hoc test after you've shown that there's significance, and then you can have it plot these groups, and that's what these little letters are here. So imagine these are 5 different simulation models that have different performance box and whisker plots here. And what the Tukey test, and that's one of popular post hoc tests, you might, if you work for an engineering firm, you might use Fisher's LSD. That's another popular post hoc test that's more popular for engineers, is that it will then label these with groups so that you can sort of see what can be told apart and what can't be. So these 3 all share the letter A. That means that these 3 simulation models can't be told apart from each other. But these 2 share the letter B, but do not share A. That means that these 2 can't be told apart, but these 2 are definitely different than these 3. So these 3 and these 2 can be told apart, even though within the group, they can't be. Now there's one that has both letters. And that just means that this kind of has group membership in both. And so this one model system, it's not significantly different from either the A group or the B group. So I can say these 2 A's are definitely different than these 2 B's. These 2 A's I can't tell apart, even though they kind of look like there's a trend. These 2 B's I can't tell apart, even though it looks like there's a trend. This AB, I can't tell if it's in which group it's in, but you kind of get the feeling that it's sort of an intermediate one here. So if your goal is to minimize your performance measure, you better pick one of these 2 simulation models, but it doesn't matter which one. Or you should use other information to determine which one. If you're trying to maximize your performance measure, you better pick these 2 or one of these 2. It probably doesn't matter which one. So that's an ANOVA with a post hoc test. And again, The output analyzer can do a post hoc test for you. JMP can do a post hoc test for you. Any stats package can do a post hoc. And that's the goal of post hoc. Does this graph make sense, what I'm saying here? I'm just summarizing an ANOVA with a post hoc test. Imagine having 5 different sims or 3 different sims. I just happen to draw 5 of these box and whisker plots on here. Are there any questions about that? Yeah. From this graph, if you were trying to say, so the one thing I can tell you is that there is a difference between the 5 simulation models. So I took this data from a different paper, but imagine these were 5 simulation models. I could say that these systems aren't all identical in performance. That's the first major thing. And then the second major thing is that I have now ranked the systems together so that even though the left system, that I'll call this system A and system B, well, I don't want to call them that, system 1 and system 2, I can't tell if system 1 has a higher performance than system 2, but I can tell that system 1 and 2 together definitely have lower performance, or whatever this variable is, than these systems 4 and 5. So if my boss was to say, give me the system architecture that gives me the lowest in this performance measure, the lowest wait time, then I would say that, well, boss, I can't tell you the difference between system 1 and system 2, but I can tell you both system 1 and system 2 have significantly lower wait times than systems 3, 4, and 5, or at least 4 and 5. So the post hoc test helps me order a large group of systems that all have variable outputs in a rigorous way. Okay. All right, now the downside of these post hoc tests is that they're not really designed for what we call sequential sampling. So the idea here is, I mentioned a couple of times that we would like to run a pilot study, look at our systems, and then figure out if we need to run more replications. And the ANOVA is not really designed for that, where you don't like run an ANOVA on 10 replications, and then based on the ANOVA results, run another 10 replications, and then run another replication. So we would like to have a way to be able to run just a few replications and then decide if we need to run many more. And there are other ways to do ranking and selection that are more well designed for that. In addition, ranking the whole group is overkill. Normally, all we care about is the best or the worst. And so we really don't need to put all of these groups. Like, we really don't need to sort this into anywhere from 1 to 5 groups. We really just need to know, of all of these, can you tell me the 2 systems that we can call the best? And everything, like, if you can't tell the difference between these systems, that's fine, just as long as I know they're the best and everything else isn't. So we really only care about the top solution there. So there are other tools that we can use that are not as full featured here, but are better matched for what we call sequential sampling, running a few replications, studying it, running a few more, studying it, and then also throwing out this idea to rank the whole thing. And if you go into the process analyzer, they've got one of it. So if you generate, so I've got 3 scenarios that I put into my process analyzer, scenario 1, 2, and 3. In this case, this is all of model 5.3. And I've updated their, these 3 scenarios correspond to different, I think I've got different call center operators operating and different capacities of the trunk line. And across these 3 scenarios, I looked at the performance variable out, which in this case was total cost. And if I go into the charts in the process analyzer and I generate a box and whiskers chart for the performance variable that I want for these 3, it has an option to say, do you want me to select the best? And if you say yes, then it will do these methods that I'm talking about, which you can read about in more detail in your textbook, where it will then color, it'll show you the box and whiskers plots and color the ones that are significantly better than all the others. So if I say I want it to select the best, it'll then ask me, is good low or high? And that's in terms of total cost, good is low. It then tells me that scenario 2 and 3 are better than all other scenarios. They can't be told apart, but they are lower than all other scenarios that I've given it. And then from there, I look at that plot, and those are my results. I know, because Rockwell's done it for me, that statistically speaking, I could recommend 2 or 3 and be fair, but I should not recommend 1, because 2 or 3 are definitely better than 1. All right, so that's what I mean by picking the best. I'm not trying to order the whole thing. I'm just trying to find out who's at the top of the order. And I can do that with far fewer replications. So if I really wanted a full ordering, I might need a lot of replications. But if all I need to do is pick the best, I can actually do that with fewer replications, and all of the intelligence has been built into the process analyzer for you. All right, so any questions about that? About what I mean by just picking the best instead of ordering the whole thing? It is possible there's still ambiguity. It might be that all of these will be red, because I might not have enough samples, and there'll be the confidence intervals will be so big that, or the box and whisker plots will be so big that I won't be able to tell the difference. But in this case, there were enough replications for me to tell the difference between 2 and 3 compared to 1. There were not enough replications for me to tell the difference between 2 and 3. Okay. All right, questions online? All right, great. Now, I've mentioned this before, OptQuest. OptQuest kind of goes, it's even more extreme, where in OptQuest, I can give it a model, and I can give it a performance variable, and I'll say, I want you to find the minimum value of that performance variable, and it will automatically crawl through every possible different step of all of your decision variables until it finds the best configuration in terms of whatever performance variable. So, and you can actually see a trajectory here. And so you can see that it started out with a certain configuration that was infeasible. It tried a different configuration. It was still infeasible, and it increased the performance output. Then it finally found a decision variables that were feasible. So they met your constraints, and then it started minimizing them. And you can drill down into them and actually see, all right, well, what decision variables did you use to get here? What decision variables did you use to get here? And so on. And so then it finally found the best one there. And it uses sort of an artificial intelligence to be able to crawl through these decision variables in kind of an intelligent way so that it can make progress, continually decreasing that performance variable for you without you having to do any effort except for set up the experiment. And so methods like this are methods that I teach about in some of my grad level courses. And so this is called simulation optimization, and they use a set of intelligence called meta-heuristics to do this. And so this is stuff that, some of the stuff I teach to the grad students and use in my own work. All right, so any questions about all of that? That's how we compare many systems. So we know how to compare one system to a hypothesis, 2 systems together, and 3 systems by using what we know about comparing 2 systems. Okay. All right, so then to wrap up today then, I want to introduce a new topic that is related to these topics, but it's going to move us in a different direction, and that's variance reduction techniques, so it's known as VRT. And so the idea behind variance reduction techniques is that we know that one way to get statistical power is increase the number of replications, how many simulations we run. And that comes because the standard error of the mean, the SEM here, the SE of our performance estimate, has a square root of R in the denominator. So if you increase the number of replications, you will decrease the standard error of the mean, thereby decreasing the size of the confidence intervals. But the numerator is important too. If we can find a way to decrease the variance coming out of our simulations, then we have another way to decrease the size of these confidence intervals. And that's what this VRT is all about here. So how are we going to use experimental design to play with this here? And we'll see there are 4 different ways we'll do that. And we're going to start today on 2 of them, and then we'll talk about the other 2 in the last, effectively the last lecture. So I'll just kind of get into this. So the first one is going to look very similar to what we already talked about today, common random numbers. That is exactly what we talked about today. So this method of VRT, CRNs, is where we use the same pseudo-random number seed into multiple parallel simulations to help ensure that those two simulations have the same input models going into all of them, the same inputs going into all of them. So I already kind of did all my spiel here, and I use a paired difference test to do this. We've seen this before in the muffin sim, and I kind of talked about it after the muffin sim back in one of your first labs, but you were doing it manually by hand. And there were two strategies, a greedy strategy and a nearly full strategy. And it's when do you move muffins into the oven and start the oven baking process? And one has to do with, well, do you just do it when any muffins are available? The other one, do you wait for there to almost always to have at least 20 muffins for a 25 muffin oven? And then you can study the performance, like the average time and system per muffin. And what I did is I had all of you end up using different inputs that were indexed by the last digit in your ASU ID. And that allowed us to run 10 different muffin schedules. So each person ran, so if your ASU ID ended in 0, you gave a certain set of muffins to the greedy and that same set of muffins to the nearly full. If your ASU ID ended in 1, you gave a different set of muffins to greedy, but then that same set of muffins to nearly full. And so there are 10 different groups of muffins that came out of that. And so when we think about the outputs here, we can't think about them independently. We have to pair them up. And so this way you can say that this here was the case where maybe this is ASU IDs ending in 0. This is what happened when you took that schedule and put it in the greedy and nearly full. Maybe ASU IDs ending in 1 was this line up here, 0, and where you give the same one to greedy, then you do to nearly full, and so on. And so we got 10 different lines here, but all the lines kind of have an upward slope, which I can summarize, and I talked about this earlier with the paired difference stuff. I can say, well, we've got, these are the ASU ID ending numbers, 0 through 9. You can also think of those as different random number streams. And so it's like I've ran the two models with random number stream 0. I've ran the two models, random number stream 1, and so on. And I got a difference. So this is model 1, this is model 2, and this is the difference between them. I can combine all those differences into one plot. And so this is maybe the difference for ASU IDs ending in 0, in 1, in 2, all the way up through 9. And I can get a mean difference. And that mean difference is less than 0. But if I were to calculate a confidence interval, what this paired difference t-test result says here is the confidence interval that I would calculate would itself be totally below 0. It would not include 0. And I know that because the paired difference t-test is less than 0.05. So I've got paired results that come out of this thing, and I just run a paired difference t-test where then my two samples are the data from system 1 and the data from system 2, and the ordering going into the paired difference t-test tells the paired difference t-test that you're going to have the same number of samples for both groups, and sample 1 will correspond to sample 1 in both groups, 2 with 2, 3 with 3, and so on. And then it'll automatically do this behind the scenes and this behind the scenes, and then it'll calculate a p-value based on whether these are significantly different than 0. That's the paired difference t-test. And if you do that, you gain a lot of statistical power. So the book's example, similar sort of thing here, they've got 100 replications and they've got an MM1Q and an MM2Q. So the difference between here is that in the open circles, you are seeing a system that has 2 servers instead of 1. And so we would expect that system to run faster. Now, when I do independent sampling, then that means that they've paired up replication 1 to replication 2 and so on, they just graphically showed them paired up, but they didn't actually run the same customers into both. And so the open circles and the dark circles here, the open circles, they got a certain customer stream. The dark circles, even though they had 2 different servers, got a different customer stream. So I don't know whether the differences I see here are due to the number of servers, 1 versus 2, or just due to the different customer streams. By forcing me to, and this is on the next slide here, for every replication, give the same customers, the same random number generator, the same random number seed to both models, then I hope you can see the difference between the models has been shrunk significantly. So if I go back here, some of these are huge differences, some have really small differences. And so the huge differences here might be due to system differences, or they might just be due to I got unlucky with the customers that were drawn for this system relative to the customers that were drawn for this system. By per replication guaranteeing the same customers going to both systems, then I don't have to worry about luck. I can say that, yeah, up here, maybe this was a particular problematic set of customers, but it's going to affect both of them. Both of them fairly get that terrible set of customers, and they both have a higher wait time or whatever this performance variable is. But there's still a consistent difference here, where I hope you can see the open circles are almost always below the closed circles. And that is going to make sense if this is in terms of waiting time, because that's the two server system, the system that processes things faster, consistently gives you lower waiting times than the one server system. So the big thing to take away here is that there is a very small difference between these systems. This small difference was totally wiped out by independent sampling. I can't tell which one's ahead, which one's behind, and the variance, just the unlucky variance of getting a different customer stream, is a much, much bigger effect than the true effect that we're looking for. But if I pair those customer inputs together, then I've extracted out that ugly additional source of variance. So all I'm left over with are the true differences between the systems. And I now can actually see that there really is a difference to having a second server, but it's a small one. So I can now estimate what that difference size is, and I can see it even though it's small. So that's what I mean. I've increased my statistical power. I've increased my sensitivity of the test by designing it this way. That's common random numbers. Now, how do you do that in Arena? You can go into the elements panel. It's the old ones, like the ones that you're using, and you can use this even with new elements, and you can drag on the seeds block. And when you drag that on, you can double click on the seeds block, and you can add a seed. And under the identifier for this seed, you can create a name if you would like, or you can just use the number, I think it's 10 is the default one, it'll say on the next slide. And if you use the default number for the stream here, this will edit the configuration for all of the random number generators used by default in your model. Otherwise, if you put your own name here, you're gonna have to manually put that in, and I'll show you how to do that on the next slide. And then under seed value, you can leave it blank. It doesn't matter. It'll do it. Its standard seed value is fine. But under initialize option, it's a drop-down box. You select that and select common. And when you do that, it will ensure that every replication has a random number seed, which is exactly, I think, 100,000 more than the previous replication. And that means that if you then run this model, if you then open up a totally new model, but it is configured the same way, then you're guaranteed that they'll use the same seed value at the beginning of every replication. And you can pair those replications together. So, so the default stream, like I was saying, is 10. So if you do a 10 there, then it'll automatically do it for all of yours. Otherwise, there is a second like whatever you run a random number generator, like Expo. If you do Expo 5, that'll give you an exponentially distributed with an average of 5. If you do Expo 5 comma something, whatever that something is after it is this identifier here. So you can actually say, I want these 3 input models to use the same common random number stream, but everything else in my system can use different streams. And so that's something that you can do there. So the simplest thing to do is just to change this to 10, and then suddenly your whole system uses common. But if you're afraid, like, well, my system draws a lot more random numbers in the post-processing, not just in the input generation, then maybe I just want to make my input streams common random numbers, and that'll help sort of guarantee that you get just the same customers, even though there's other random things going on in the rest of your system. So that's how you can do it in Arena, and this is me showing you you can do Expo 5 comma, and then the second argument is the stream. So if you leave that out, it defaults to 10. If you put it in, it's whatever identifier you want there. And then that will generate these that will generate these CRNs. And so, and this is just me summarizing that. And so now if you've got model 1 and model 2, they both have performance data coming out. You can go into the output analyzer, you can load in both of those streams, and you can say, I want to compare them using a paired difference t-test. Or you can load them into JUMP. JUMP has a paired difference t-test. So you go into JUMP and you say, I want to do a paired difference t-test. It says, what are your two inputs? And you say, here's my performance data for model 1 for 100 replications of it. Here's my performance data for model 2, 100 replications of it. And then JUMP will do a paired difference t-test on those 100 samples versus the other 100 samples. And then that's the way you capitalize on this CRN. The downsides of CRN basically is that we don't know if it works. So it usually works, but the only way you can kind of guarantee that it works is by running a pilot study where you compare your variance before and after you do CRN. So you could say, I'm going to run my 10 replications independently from the other 10, or I'm going to run them with the same pseudo-random number generator seeds, and I'm going to see if I get an improvement. Most of the time you will get an improvement, but if your systems aren't really properly correlated, so something that's difficult for one system is easy for another and vice versa, then CRNs aren't going to work for you. So you kind of do need to do a little bit of a pilot study with CRNs. All right, so that's our first kind of VRT. Are there questions about that? This general idea of using the same random number seed in two different models to help eliminate variance and increase statistical power. We're introducing positive correlation between models. All right, well, in that case, let's just do an attendance exercise. And that's all I'm gonna do for you today. And so the question that I will give for you here is, what sort of correlation does CRN depend upon inducing between models, positive or negative? So I just said that in CRNs, they only work if you have a particular correlation between your two models. In other words, if I give the same inputs to the two models, if it's a difficult input, then I need both models to behave certain ways. And so the question here is, do I want them to be positively correlated or negatively correlated if I want CRNs to work? And again, these aren't graded for correctness, they're just kind of graded for completion. And that's all I've got for you. So the next time we'll see each other is Tuesday, and next week is otherwise a short week where Thanksgiving is the Thursday. And then we'll come back and we'll be in the final week of the class. All right, if anybody has any questions online, I'm happy to take those as well. Otherwise, that's all I've got for you. And have a nice weekend. You give me 1 second here to